Yes, ma'am.
Okay. So, yeah, all the topics have already been covered in the other revision sessions, but we'll start off with orthogonal transformations because Shubhajit had mentioned that we'll start off with that in the next session. And then, yeah, Krishna sir had requested just a recap of weeks 9, 10, and 11. So let's not get into the concepts or anything. We'll just write down the formulas or the conditions that are being used in solving problems of week 9, 10, and 11. And then, yeah, the affine mapping. There was a request for affine mapping. So we'll just quickly do all this. And in case you have any other doubts, we'll solve that as well.
And there's
Okay,
a
so
question.
first, what is it?
Just asking, like, is there stats 2, we have a weightage system, like for the 9th and 11th, that's for 70% and the rest of the syllabus is 30%. So it's like in maths 2 as well, like something like that, or it's like random, we can get a question from anywhere, from the any week.
Actually, we don't want to reveal weightage because every question is like connected to more than 1 week. Like for
Okay.
example, if I ask you to find the dimension of a vector space, to find the dimension, you'll need the week
Got it.
5
Got it.
content,
Yes.
and then
Yes. Yes.
yeah,
Yes.
you
Yes.
have to
Yes.
find the basis, and to find the basis, you have to solve a system of linear equations and all that. But anyway,
Yes.
you can roughly think of as quiz 1 and quiz 2 portions 50%, and after that 50%.
Okay.
Like
Got it.
Shubham had put a post on Discord, so that's why we are telling this,
Thank you.
that
Thank you.
you can take it roughly, approximately, not like you
Approximately.
cannot
Yeah.
exactly divide, but yeah.
Okay, ma'am. Thank you.
Okay.
Ma'am, can we ask a previous of 8 weeks as well in this session?
Yeah.
Yeah.
So let's
But
discuss all
after,
these and then
after that, yeah.
yeah.
Sure.
We'll quickly do this maybe for an hour and then we will take questions.
Yes, ma'am, please. Because
Okay.
we have also taken this 2-3 weeks ago. So,
Okay. Okay, fine. So what is an orthogonal transformation? When do you say a transformation, a linear transformation on a vector space is orthogonal?
Dot product is 0.
No. That dot product is 0 means the vectors are orthogonal. That's right. But we are talking about an orthogonal transformation now.
T of V1 plus V2 equals to V1 plus V2, right?
No.
Ma'am, sorry to interrupt. I just had one question.
Dot product of T of V1, V2, I think.
Yeah. So the inner product of
T1,
inner product
V2
Tx,
equals to inner product of V1, V2.
Yeah.
Right.
Yeah.
This should be true for all vectors V1 and V2. So yeah, we had written V comma W. So let's follow that only. V and W. Yeah, V1, V2 is right, but yeah. So inner product of the images of two vectors should be equal to the inner product of the vectors itself. So whatever is the inner product that is defined, it's not necessarily the dot product, whatever is the inner product that is defined on the vector space. So we start with V and inner product space. So a vector space along with an inner product. So if the inner products are preserved, then the transformation is said to be orthogonal. And if the vector space, the inner product space is Rn, then we usually take the dot product. So TV dot TW should be equal to VW. So if we take the inner product space as Rn with the dot product, then this is the condition that we have. And from this, we can talk about, when we talk about the dot product, we can talk about angles, lengths, and all that, right? Using dot product, we know how to find the angle between two vectors or the length of a vector and all that. So yeah, in that sense, an orthogonal transformation preserves lengths and angles. That is what happens. So because of this, the images, the dot product of the images being equal to the dot product of the vectors itself, it actually preserves lengths and angles.
Ma'am, for orthogonal transformation, we'll mainly be focusing on dot product for inner product, right?
Yeah, if the inner product space is Rn. Yeah, in whatever examples we have discussed, it has always been Rn with the dot product.
Yeah.
Yeah, sorry not to disturb. I just had one question. That are we going to have anything revision regarding 9 to 11th week?
Yeah, we will just quickly recall the formulas for those weeks. Nothing conceptual.
Okay.
Yeah.
We are not going to be asking questions.
Yeah, we will. Means for the first 1 hour, maybe we will discuss orthogonal transformation, weeks 9, 10, 11, quick recap. And then someone had asked for affine mapping. So after this, we will go to questions. Means we will take questions on any topic throughout. And in between, if it's related to the concept that we are discussing, you can ask doubts as well. No problem. Okay. So we have a transformation, and then we have a matrix related to a transformation with respect to a given basis and all that. We can write down a matrix. So a matrix is said to be an orthogonal matrix. Orthogonal matrix if this is satisfied. A transpose is equal to A transpose A is equal to identity. So in this case, we are always considering A to be a square matrix. So it is a square matrix of order n. Rn cross n means it is a n cross n matrix with entries in R. So yeah, if this condition is satisfied, then the matrix is said to be an orthogonal matrix, and the matrix of an orthogonal transformation will be an orthogonal matrix. Okay, so yeah, we know a lot about orthogonal matrices, right? What is the determinant of an orthogonal matrix?
Zero.
No, this is an orthogonal matrix.
Oh, sorry.
Is it 1?
Plus minus 1.
Yeah, it's plus or minus 1. Yeah, because determinant of A transpose is equal to 1. Determinant of either identity matrix is 1. So this is nothing but determinant of A into determinant of A transpose. But determinant of A transpose is equal to determinant of A. So determinant of A whole squared is equal to 1. So the determinant of an orthogonal matrix has to be plus or minus 1. So an orthogonal matrix is always invertible. And this is what happens. And when this happens, do you remember I had discussed in my live session of this week that what does it mean when A transpose is identity?
Column will be orthonormal.
Yes, madam.
Okay. Is it the column or row? I need to check.
So is row, yeah.
Row, I guess, right?
Yes,
the rows
Yeah,
are
yeah.
Rows.
Yeah.
rows are orthonormal. They should all be unit vectors, and they should be orthogonal to each other. If this happens, then A transpose is identity, and A transpose A is identity means that the columns are orthonormal.
Yes, ma'am.
Yeah. And for an orthogonal matrix, we are considering only square matrices. So the rows and columns are orthonormal. That is why both these conditions are satisfied. A transpose is identity and A transpose A is identity. And not just that, if one of these conditions is satisfied, the other is automatically satisfied. That is also clear, right?
Yes,
If
ma'am. Yeah.
A transpose is identity, this if and only if A transpose A is identity. This is true only because A is a square matrix. For rectangular matrices, this doesn't hold.
Yes, ma'am.
Yeah, because it's a square matrix, we can talk about the inverse in this case, and that is how we get this result. Okay. Yeah, so this is all with respect to orthogonal matrices. And then we have a special set of matrices which are orthogonal, that is the rotation matrix. So what does the rotation matrix do, or the rotation transformation? What does it do? What does a rotation transformation do? You have two
It
vectors.
rotates all vectors in with an angle theta.
Yeah. So if I denote r theta as the linear transformation, or t theta as sir has used, the transformation the rotation transformation, it is just going to rotate the vectors by an angle theta. So if this was u, then this is going to be theta to get tu. And if this was v, then this angle is theta and we get tv. So what the rotation transformation does is nothing but it rotates the vectors by an angle theta. Does the length change in this case?
Neither the length nor the angle between vectors changes.
Yeah, that's it. So because the angle between the vectors don't change, it is an orthogonal transformation, right? So if you take inner product tu with tv, that's going to be equal to inner product u with v, because you're just rotating this setup by an angle of theta. So the inner products are going to remain the same, and hence the rotation transformation is orthogonal. This is an example of an orthogonal transformation, and the matrix of this transformation is what we denote by called the rotation matrix. So it is a rotation matrix. And what is the 2 cross 2 rotation matrix?
Sin theta, cos theta minus theta.
Yeah. Minus sin theta,
Sin theta, cos theta.
Yeah. Yeah. So if you needn't remember this, actually what happens is, okay, if it's 2 cross 2, then we are dealing with R2 to R2. So I need to, what is happening here? T theta. I'm rotating the vectors by theta. So how will I find the matrix of a linear transformation? Take a basis for the domain, codomain and all that, right? To write down the matrix of a linear transformation, we want a basis for the domain, codomain and all that. So let's take the standard ordered basis. 1, 0, 0, 1. So what is t theta of 1, 0?
It's cos theta sin theta.
Yeah, 1, 0 is here. When it's getting transformed, it's going to go to some position where the angle is theta from the original vector. So now this is my new vector. This is t of 1, 0. If this angle is theta, I know what this coordinate is. It's cos theta, sin theta. Cos theta, sin theta. What happens to 0, 1? This one?
Minus sin theta, cos theta.
Yeah. 0, 1 also gets rotated by an angle theta. So the original vector is here. This is the resulting vector. So this angle has to be theta. So that is nothing but cos of 90 plus theta, comma, sine of 90 plus theta, right? This is how we write any coordinate, right? The angle is taken with the positive x-axis. So this is 90 degree plus this angle theta. So cos 90 plus theta is minus sine theta, and sine 90 plus theta is cos theta. Okay, so now when I write down the matrix, this is what? Cos theta times 1, 0 plus sine theta times 0, 1. Similarly, this is minus sine theta times 1, 0 plus cos theta times 0, 1. So cos theta, sine theta, minus sine theta, cos theta. So this is the 2 cross 2 rotation matrix. Even in case you don't remember where the minus sign comes, you just remember this procedure. You know
can
how
you,
to find.
yes, can you please explain these two lines once again? T theta
Okay.
1, 0 and T theta 0, 1.
Okay. So what does t theta do? It rotates the vector by an angle theta, right?
Yes.
Yeah. So 1, 0, this vector gets rotated to some vector which is at an angle theta from the original vector, right?
Yes, sir.
Yeah. So what is the coordinate of this point?
Cos theta, sin theta.
From which point? Right? This is cos theta, sin theta, right?
From which point?
No, the resulting vector. This is going to get transformed into some other vector.
Oh, okay.
What is this?
This is cos theta, sin theta.
Yeah, cos theta, sin theta. That's what I've written here. And that can be written as in terms of the basis vectors again. So it's the standard ordered basis for the codomain as well. So it can be written as cos theta times 1, 0 plus sin theta times 0, 1. And then t theta of 0, 1. This gets rotated to some vector which is at an angle theta from the original vector. So how do we get this point?
Minus sin theta cos theta.
Yeah. You can directly write it as minus sin theta cos theta, or this angle. How do you find that point is angle made with a positive x-axis, that is 90 plus theta. So cos of 90 plus theta, comma sin of 90 plus theta, that's minus sin theta cos theta. And we put it down as a matrix. That's it. Is it clear now?
Yes, ma'am.
Yes, ma'am.
Okay. Fine. So this is the 2 cross 2 rotation matrix. That is when the transformation is from R2 to R2. This is the rotation matrix that we have. And okay, what is R minus theta?
It is
I replace
transpose
theta
of,
with minus theta.
yeah.
So cos is an even function, so it's going to be cos theta. This becomes minus sin theta. This becomes sin theta, and this becomes theta. So this is the transpose of what we had. Yeah, and you can check that r theta, r minus theta. What does r theta do?
It rotates by angle theta. So r then r minus theta would rotate it back by angle theta.
Yeah.
So I.
So this is going to be identity, right? Similarly, r minus theta, r theta is also going to be identity. But we know r minus theta is r theta transpose. R theta transpose, r theta is identity. R theta transpose is identity. So we know that the rotation matrix is an orthogonal matrix. Right? Is it clear?
Yes, ma'am.
Yeah. So when we go to the 3 cross 3 case, that is when we consider the rotation matrices, the rotation transformation from R3 to R3, things become a little complicated actually. But for the sake of this course, you can easily think of only one point of view and we can write down the matrices. So along the z-axis, if I want to rotate along the z-axis, so I have the x, y and z-axis. If I want to rotate along the z-axis, what happens? Is there some change in the z coordinate when I rotate along the z-axis?
No change in z coordinate.
It rotates along the xy plane.
Yeah. So there is no change in the z coordinate. That's going to remain same. Only these xy coordinates are going to move somewhere
They
else.
have to fit that rotation matrix in x and y coordinates and make z equal to y.
Yeah,
and then in the
there is
remaining,
no
we put
change
the
in the z. There is no change in z. So you just put that as the unit vector along the z-axis. And then you fit in the r theta 2 cross 2 matrix here. When we rotate along the x-axis, what happens?
It will be 1, 0, 0.
No change in x coordinate. And here there is no change in z coordinate. So here 1, 0, 0, 0, 0. So you fix the x unit vector along the x axis in the position for x, and then you write down the 2 cross 2 rotation matrix here. And you do the same for y as well.
1 will be in the center.
Yeah.
Ma'am, could you just mute all these? Some sort of disturbance.
Sure. Okay, so in this case, 0, 1, 0, 0, 0. So this is how it's going to be. And then in the remaining portions, the 4 slots, r theta is going to occur. So that's going to be cos theta minus sin theta, cos theta. So you can easily remember the 3 cross 3 rotation matrices like this. Along which axis you want to rotate, there won't be a change in whatever axis you're rotating, in that corresponding coordinate, there won't be a change. So that will be fixed like this using the unit vector in that direction. And in the remaining 4 slots, the 2 cross 2 submatrix will be the rotation matrix of order 2. So is it clear what a rotation matrix is, how we get it?
Yeah.
Okay. So orthogonal transformations, orthogonal matrices, and rotation matrices as an example of orthogonal matrices is done. You have any questions in this? We can take that now.
Ma'am, hello ma'am.
Yeah. Yeah.
Ma'am, we have taken a standard order vector here, but suppose we take any order vector, any order basis, then what should we do in that case? How do we get rotation matrix regarding
So
that order?
you can take any basis and then you can find the corresponding matrix of a linear transformation. But this is the matrix we call the rotation matrix. So when you take the standard ordered basis for the linear transformation, the matrix that you get is called the rotation matrix. If you take some other ordered basis, you're going to get some other matrix, which will be similar to this matrix, but this is what we call the rotation matrix. When we take the standard ordered basis, whatever matrix we get, that is called the rotation matrix.
Okay.
Yeah.
Any example can we solve?
Yeah. Example for what? Orthogonal transformation, is it? Or?
Yeah, 8.5. Yeah.
Ma'am, that sin minus sin theta, is that the standard order, like cos theta minus sin theta and then sin theta cos theta? Do we need to remember this, or the sign convention, is it minus?
Yeah, when we take the standard ordered basis, we get cos minus sin cos, right? So this is the rotation matrix.
This we need to remember this one, right?
Yeah.
Okay. Okay.
How you got this matrix cos theta minus sin theta?
I had explained this twice actually. Did you join late?
I understood that we have taken that standard order basis, but then we have taken rotation of that I know that.
Okay, so what does the rotation transformation do? It's going to rotate the vectors by an angle theta, right? Yeah. So if we take this vector 1, 0, if we take this vector and rotate it by an angle theta, what is the resulting vector that we are going to get? What are the coordinates of this resulting vector?
Comma sin theta.
So we know from physics, right, that it's going to be cos theta sin theta. That's what I've written here. Similarly for this vector, when we rotate it, I'm going to get this vector, which is at an angle theta from here, from this vector. So the total angle is 90 plus theta. So that's going to be cos 90 plus theta, comma sin 90 plus theta. Is it clear?
Yes. Yes, ma'am, it's clear.
Okay, fine. What does this ask for? Okay.
I think solve with us.
Yeah. Okay, so the first example here, T1 of x comma y, it's given as x plus y by root 2. T of x comma y is x plus y by root 2, comma x minus y by root 2. So how will we check whether this is an orthogonal transformation or not?
Ma'am, inner product, we need to find it out for this.
Yeah. So we need to take two vectors, x1, y1 and x2, y2. Take the inner product of the images and then you have to check whether that is equal to the inner product of these two vectors. So it's given that it is usual dot product where the inner product spaces with respect to the dot product. So it's the normal dot product. You just need to calculate this, evaluate this, evaluate this. And if these two are equal, then it is an orthogonal transformation. That's it. And if they are not equal, it is not. Maybe if we remove this root 2, now is this an orthogonal transformation or not?
No, ma'am.
Can you give two vectors for which the inner product is not preserved?
1, 2, 2, 3.
I think any vector should work.
Yeah.
1, 2, 2, 3. So what is this? This is inner product. What is image of 1, 2? 3, comma, minus 1, comma, 2, 3. 5, comma, minus 1. So the inner product is 15 plus 1, 16. What is inner product of 1, 2 with 2, 3? 2 plus
6, 8.
8.
Yeah. So these two are not equal. So when we remove that divided by root 2, it is actually not an orthogonal transformation. Because for an orthogonal transformation, we want A transpose, the matrix, to satisfy these two conditions, right? So if these conditions are satisfied, then the rows and columns should be orthonormal vectors. That divided by root 2 was actually making the norm 1. When we removed that, that was like this is being disturbed.
Ma'am, is it sufficient to just check what we've just done for checking whether it's an orthogonal transformation?
No, here we are telling it is not an orthogonal transformation.
Yeah,
To
so
show that
this is sufficient. This is sufficient.
Yeah, yeah. To show it is not, you just need to give one counter example, right? Because if it is an orthogonal transformation, this should be true for all vectors. Even for one set of vectors, this is not true, then it is not an orthogonal transformation, right?
Yes, and if supposing this condition is met, then do we have to go to the orthogonal matrix and check that? Whether
No. See, are you asking if for these two vectors the condition is satisfied?
No, in this case it's not satisfied, but if it was satisfied for some reason, in some way,
okay,
yeah, like
let's do this. So in this case, we will have divided by 2. So this will be 8. Just because these two are equal, you cannot tell that this is an orthogonal transformation, because only for this set of vectors it is satisfied. You need to check for all vectors. So if you want to show that it is an orthogonal transformation, you have to take general x1, y1, x2, y2. If you want to show it is not, then one set of vectors is enough. So in this case, you would do this.
In this case, is it? In this case, is it?
In this case, yes, it is. It is an orthogonal transformation. Means you can check that it is an orthogonal transformation.
I'm sorry, I seem to have forgotten. How do we check now? Next step.
Yeah, you do this. You evaluate this and then this. You first find out what is T of x1, y1. What is T of x2, y2. And then inner product of these two. What is the inner product of these two?
x1 plus y1 into x2 plus y2 upon 2. X1
and the
comma
other
x
term, right?
Plus, yeah.
By 2. So you have to expand this and then you have to check whether that is equal to this. It will be equal.
Okay, that's sufficient to check the general case.
Yeah, this is what you have to do. This is using the definition. You can choose a set of vectors and show that they are not equal to say it is not an orthogonal transformation. But to show that it is an orthogonal transformation, you have to do the general case. Means you cannot choose vectors because the definition has to hold for all vectors.
So, ma'am, we don't have to go ahead and find the transformation matrix and check whether A transpose is equal to I.
Oh, this is the definition, right? Once you have done this, the matrix of the transformation is going to be orthogonal. You needn't
In
do
any
that.
case. Okay, in any case.
Yeah.
Okay. Thank you, ma'am.
Okay.
Madam, if
So
I'm
maybe
not if I'm not actually asking you to digress, would you be able to help me with activity 8.3 question 5, madam? Or maybe
what is it about?
it's projection basically.
Okay. 8.3 question.
Question 5. 4 came all
Okay.
right, but this one is where I was stuck.
Okay. So how did you do the fourth one?
Fourth one is basically we go for
You know the formula.
Yes,
You
yes,
just
formula.
put it,
Yeah.
right? Yeah.
Yeah. Yeah.
So here the direction is given straight away. Here you have to find the direction perpendicular to 3, 4, right?
Correct.
How will you find, when do you say something is, a vector is perpendicular to 3, 4?
Dot product is 0.
0.
Not dot product, the inner product that is given in the question, right?
Oh, sorry.
Inner product is 0. Yeah.
Did you do that correctly or did you use the dot product?
I think I got stuck at where when it was asking for perpendicular direction projection, I was stuck at the place where how can I get a projection in the first place? Yeah.
So here A comma B, A is a vector, B is a vector. So your A is 3 comma 4. You want to find a vector B such that inner product of 3 comma 4 with B is 0. So inner product of A 3 comma 4 with B will be something like this. You expand,
yes,
and then you have to put it equal to 0. And that is what you have to check. So that's going to give you the perpendicular direction and then use that formula here. Can you quickly tell me what that inner product is? A1, B1, and then?
Minus A2, A1, B2.
Minus A1, B2.
Minus
Minus
A2,
A2, B1.
A2, B1.
Plus
Plus
4
A2,
A2,
B2, B2.
Okay.
So
So you want to find,
It's A2, 4 A2, B2.
Oh, okay. A2, B2. Okay.
Yeah.
So you want to find this, comma B1, B2 should be equal to 0. So 3B1 minus 3B2 minus 4B1 plus 4 4s are 16B2 should be equal to 0. Minus B1 plus 13B2 should be equal to 0. 13B2 should be equal to B1. Yeah. So you're looking for vectors that satisfy this. 13B2 comma B2. What will be the unit vector in this direction?
Unit total with 13, that is 169.
13 square is 169.
169 plus
170.
170.
170 B square.
Yeah. So it's going to be this 170 B2 squared.
B2 square.
Yeah. The good thing about options is you have to first check if this is satisfied. Means the projection is going to be along this direction, right? So you will be multiplying some number with
some scalar.
This. Yeah. So obviously the first and second options don't satisfy. The third one also doesn't, or only the third one satisfies. The second coordinate should be, the first coordinate should be 13 times the second coordinate. And
they both should be positive or both should be negative.
Yeah. So easily you can eliminate from the options, but yeah, you can proceed from here. You can use the value of x and then actually get the vector.
Okay. Thank you, ma'am. Thank you.
Okay.
Yeah. What about fourth, madam? How will they resolve that fourth one parallel line?
This is formula. You have a formula, no? Projection of a vector in the direction of another vector. What is that? Projection of u in the direction of v is?
Inner product of u and v in the direction of unit vector v.
In the direction v. Yeah, right.
V cap.
So, yeah, v cap, or you can divide v by norm of
this
v.
I know. How to solve the fifth question? I mean, in a direction perpendicular.
Yeah, that's what we did here, right?
That is done.
We first found the perpendicular direction, and then we found the answer. Means this is the perpendicular direction. Now you have to use that given vector and then find out.
Excuse me, ma'am.
Yeah.
Ma'am, actually it's an emergency. Ma'am, I'm extremely ill, and I will be admitted to the hospital tomorrow, and I'm having jaundice. So, ma'am, in this case, I will not be able to take end term exam. So, what are the possibilities? What can I do now?
You can write the end term alone next term.
Okay, ma'am.
You have that option of not repeating the course, just appearing only for the end term.
But ma'am,
but you have to do that immediately, means the next term only. You cannot skip a term.
Okay, ma'am. Math 2 and English are my two last courses. So, in the next term, will I be eligible for diploma?
I'm not sure about that. You have to write to support about it.
You need to complete foundation.
Yeah, you need to complete foundation to enter.
Suppose anyone is not able to give the end term, but he can continue the foundation next term and along with that appear in all the 4 courses, say, in the next term, when the end term for the next term is going to be in December.
You can choose.
No,
you can write to support about this.
Yes.
Yeah, they will help you with this.
Okay,
you can mention your situation. And
sir, could you explain limit and continuity?
Thank you.
Yeah, I'll do that. Yeah, so you please take care of your health first.
Yes, ma'am. Thank you.
Okay. Okay, maybe we'll quickly do recall week 9, 10, 11 so that, and we will discuss limit and continuity there. Okay,
Madam,
so yeah.
Madam, could you explain one question which is in graded assignment 6, regarding rotation matrix, rotation orthogonal?
Graded assignment, which question?
I don't know. Rotation XYZ.
Okay.
Yeah.
Okay, if V is this vector, ABC is a vector, obtain command. Okay, YZ plane with angle 60 degree above. Just substitute the formula, no? We discussed the formula. Theta is 60 degree here. It's about x-axis. So use that matrix, plug in 60 degree instead of theta.
Okay.
And then if you want to find the image, you just multiply by this vector, right? Once you get the matrix, once you know the transformation, TV is the image. Yeah.
Multiply with column vector of 1,
1, 2, 2. Yeah.
Ma'am.
Okay.
Ma'am,
yes.
Can you help me with a question?
Yeah, which question?
Ma'am, I think I forgot to find the basis. Can you do a question for me, ma'am? 4.1, question number 7.
Okay, can we do that after we revise week 9, 10, and 11? Maybe by then you can go and watch
I thought
live.
that it would not take a lot of time, so I asked.
Did you watch any live session to recall or?
Yes, I tried.
Lecture. Basis for what? Which question were you talking about?
7. This one.
By matrix you can do.
This is simple, right? What is the dimension of R2? What is the
It's
dimension?
1, 0, ma'am. We can go for it is 2. We should have two vectors in the basis.
Yeah, dimension is 2, so you can have maximum 2 vectors.
But
Okay.
both are
And
must
then
be
you have to check
independent.
whether both are linearly independent or not.
Independent
Yeah,
or not.
Okay.
so the first one cannot be a basis because it has 3 vectors. The second one, yes, it is linearly independent. Third one is also linearly independent. So,
ma'am, in this way we can check. But suppose it is given to find the basis. Then how to do that? I was not able to do. I thought I forgot.
This one. So you have a subspace. You want to find a spanning set which is also linearly independent, right?
Yes.
Can you tell me what is the dimension of this subspace?
Minimum spanning set.
Can you tell me what is the dimension of this subspace?
2. Because 2
The person
independent
who asked the doubt, can you please tell me that?
Yes, ma'am. 2.
So what is the dimension here?
2.
Why is it 2?
Because
you need to check. You need to revise previous. You need to saw previous 5 sessions, which are, that will be clear. Otherwise,
yeah, or maybe you can just watch the revision session for quiz 1. That's completely this. So you just have to watch one.
Shubhodh sir already discussed. You can see.
Just check the session
Second
which
division.
happened on I think Monday or yeah.
Subhajit explained very nicely. Just watch second revision. That is sufficient till week 6. You can easily manage.
That is true.
Please continue with the week 9, 10, 11 because I think it is 50% weightage.
Yeah. So we will just recall the thing, what formulae and all that, whatever is needed. Okay. So week 9, what is a multivariable function?
Function dependent on 2 or more.
More than one variable.
More than one variable, like x, y, z.
Yeah. And when do you say it is scalar valued?
When it's from Rn to R.
Rn to R and Rn to Rn.
Yeah. So when the codomain is R, when the output is just a number, it is called scalar valued. When the output is a vector, that is when the codomain is in Rn, where n is greater than 1, it is a vector valued function. So if you have something like this, f of x comma y is equal to say some number u. Okay, say alpha. Then this is a scalar valued multivariable function. Instead, if I have something like this, then this is the vector valued multivariable function. Okay, so in the case of scalar valued and whatever, in the case of a multivariable function, since we have the function being dependent on more than one variable, when we talk about derivatives, the question of with respect to what variable comes into picture. So that is where we have partial derivatives. What is the partial derivative? If I have a function.
Last sentence once, please. That went a little fast.
What did you just say, sir?
I was just asking you to repeat the earlier sentence. I was just trying to note down.
Okay, so I was telling if you have a function dependent on more than one variable, when we talk about the derivative of such a function, the question of derivative with respect to what variable comes into picture. So that is why we have partial derivatives. So you can differentiate the function with respect to x or with respect to y. And when that happens, when you find the partial derivatives, if you differentiate with respect to x partially, it actually means that you're keeping all other variables as constants and just differentiating, doing usual differentiation with respect to x alone. And the partial derivative with respect to y means that you're keeping every other variable constant and differentiating with respect to y alone. So yeah, you know how to find the partial derivatives. But anyway, let me just write down the definition for fx. This is change with respect to x alone. There is a change only in the x coordinate. Y coordinate remains a constant. This is the formula, the limit formula for definition for the partial derivative. Similarly, with respect to y, there will be a change in the y coordinate alone. X coordinate will remain a constant. Okay. And what is partial derivative? What does fx mean? What does this say? Rate of change along x direction, right? And fy says rate of change along y direction. What about the infinitely many other directions that are there? We know this one, this one. What about the other directions? That is when the directional derivative comes into picture. So we always treat directions as unit vectors. So the rate of change of a function along any direction u is the directional derivative along that direction. And what is the formula for that, or the limit definition?
X plus
f of x plus h comma
plus
y plus h
HU1.
minus.
Yeah. So the vector x comma y has to be added with the vector u, the whatever is the unit vector. Yeah. So there'll be a change with respect to both directions. Minus f of x comma y by h. Or yeah, we can write it as f of x plus hu1 if u is equal to u1 u2 comma y plus hu2 minus f of x comma y by h. So this is the directional derivative. But later on, once we studied gradient, we know that the directional derivative is nothing but the gradient of the function dot product with the unit vector, right?
Yes.
Yeah, ma'am, only the
So
partial
this is
derivative
a
is
much
continuous.
simpler way. Huh?
Only if the partial derivative is continuous at that particular point.
Yeah. When the
Yeah.
gradient is, the function is continuous at that point, then only we use gradient formula.
When the gradient is continuous, not the function. Continuous at whatever is the point of evaluation. So yeah, this is a much simpler way to evaluate the directional derivative. And what is the gradient?
fx comma fy.
Yeah, it is the vector of all partial derivatives. Since here we have a function of two variables, it's just going to be fx comma fy. So if the gradient is, yes.
Ma'am, if fx and fy are both continuous, then the gradient will be continuous, right?
Yeah, the gradient is continuous means the gradient is a function, right? This is a function, right?
Yeah.
Fx is a function, fy is a function. So the gradient is a function. When we talk about continuity of the gradient, we are talking about continuity of this function. And continuity of multivariable functions is treated component wise. So each component, if it is continuous, then the function is continuous.
Okay.
So how do you find the limit actually? Limit of multivariable functions. Limit as x comma y goes to x naught comma y naught f of x comma y. How do we do this? In the single variable case, we just had left hand limit, right hand limit. Yes. But here we have infinitely many ways to approach this point. So the limit exists only if all the limit along all the directions is equal. Only then the limit exists. Okay. So how to find the limit and all that is a tricky topic. But in our course, we are mostly dealing with functions where we have like you can split the limits and all that. Limit of f plus or minus g is limit f plus or minus limit g. In case they exist, limit f, limit g and all exist. So all these using such tricks we have been solving and all that. So to find the limit, in case you get 0 in the denominator, what you do is you see if the function is you can simplify the function such that the denominator doesn't become 0. And if it is still not becoming non-zero, then try to check if the limit does not exist. That is, find two different paths along which the limits are different. And in all the examples in our course, mostly we are okay, means just with y is equal to mx, y is equal to mx squared, y is equal to m root x, and all these simple curves, we have been getting that the limit does not exist. We haven't seen functions for which this did not work.
Ma'am, in
the job.
Ma'am, in an earlier session when we had originally done this particular part of limits, you had given a trick that if the numerator's degree is more than or less than something of that sort, could you just mention that hint that we have that would give us some indication of whether the limit exists or not? You had talked about the degree of the numerator being more than the denominator, then most likely the limit exists and vice versa.
Okay, actually in that session, in that flow, I would have spoken something, but anyway, let me, yeah. So yeah, someone asked me to repeat, so I just repeat.
Hello, ma'am.
Yes.
For limit does not exist, that is that we can find, but how do I find a limit is exist? That is the most important, I think.
Yeah.
For continuity, I need to check limit is exist or not.
Yeah, showing that limit exists is not an easy task, and we haven't studied the actual, means the entire concept of limit, how to check whether the limit exists in this course. So from this course's point of view, whatever we have dealt with are all simple things. So that is enough. You needn't get into like very complex functions. Yeah.
Okay, ma'am.
And to show that,
yeah, presently limit exists, we can know, madam, how to find continuity for this particular.
I'll come to that. So yeah, I'll just repeat
And
this.
could you please brief partial existence of partial derivative also?
Existence of partial derivative just means that the limit exists. This limit.
Exist means it should be 0 or not 0?
No, exists. That's it. It can be anything.
Ma'am, if partial derivative 0 by 0 means 0 by 0 form, then it is not defined, no?
Yeah, you have to do something more to check whether it exists or not. You cannot leave it at 0 by 0. Means you have to show that it does not exist or something. Means this limit does not exist. See, what is this? Is this a one variable limit or multivariable limit? This one.
Multivariable limit.
No, this is a one variable limit. H is a number, right?
Okay.
So here you just have to calculate left hand limit, right hand limit. If they both are equal, then the limit exists. If they are not equal, the limit does not exist. That's it.
No, ma'am, is partial derivative 0 by 0 form.
Yeah, this is the partial derivative, right?
No, ma'am. एक और तरीके से निकालते ना.
Okay. And then
definition
for 0 by 0, you can't do that. You need to go to
when it is in the 0 by 0 form, you cannot do that. You have to go by the limit. The definition using
y is equal to x and y is equal to x.
No, to check the existence of partial derivative, whether we get 0 by 0 form, something like that, how to conclude whether it exists or not, partial derivative?
See, you have to check why you're getting that 0 by 0 form. See, limit as x goes to 0, x squared by x. Here also you'll get 0 by 0 form. So you have to check why you're getting that. You have to keep it in the simplest way possible. And then you have to try to evaluate the limit. So if you're getting 0 by 0 form, there may be a way to eliminate that. To eliminate that possibility of 0 by 0. So depending on the... No, you cannot
Actually,
apply
after this, one question, could you please explain weekly mock question number 4 relative to partial derivatives?
Okay, yeah, I'll do that. Before that, yeah, let me just recall what limit is again. So what is limit? You're approaching a point, means you want to find the value of the function as the values, okay, if you want to find the limit as x comma y goes to x naught comma y naught, what you're doing is you're seeing how the function behaves around this point x naught y naught. And because we are in the multivariable setup, there are infinitely many ways to reach the point x naught y naught. So the limit exists if limit along all the infinitely many directions is equal, and checking along infinite directions doesn't make sense. So checking that the limit exists is actually a tough task, but showing that the limit does not exist is much easier, because you just have to find two different paths along which the limiting values are not the same. So if they have to be the same if the limit exists, if they are not same along in even any two paths, then it means that the limit does not exist. So showing limit does not exist is much simpler. And about the power thing that I was talking about in that live session, I think it will be better if you just watch that live session again, because I might tell things which are not correct and it might be confusing.
Okay, ma'am.
Yeah, because I need to recall and means I have to think.
It's okay. It's
Yeah.
okay, ma'am. Thank you.
Okay. Let me just finish continuity, definition of continuity, and then take that weekly mock question. Continuity is...
Can I interrupt just once, madam? You just mentioned laptop rule is not applicable at all scenarios. Can you just tell where it is applicable? It is easier.
It is applicable only for one variable calculus. There is no L'Hopital's rule in multivariable calculus.
Okay, so thank you. Thank you. That's all.
Yeah. To check if
can
a
you
function
take an
is...
example of limit?
Yeah, I will. So to check if a function is continuous, first of all, the value of the function at that point should be defined, and the limit as we tend to that point should exist. And these two values should be equal. The third condition is the limit should be equal to the value of the function at that point. So if these three conditions are satisfied, then we say that the function is continuous. Okay, so let's maybe take that weekly mock question.
Week 9 and 10, question number 4. Question number 4, could you please solve the last option?
Okay, so this is the function. It has a different definition at 0, 0, because at 0, 0, the denominator becomes 0. If we go by this definition. Okay, how do you check whether the partial derivatives exist or not? How will you calculate the partial derivative? So for x comma y not equal to 0, 0, there is no problem. You just use the quotient rule and find the partial derivatives. But at 0, 0, you have to go by the limit definition, right?
Yes.
Yeah, because you cannot just like that. Means just because f of 0, 0 is 0, you cannot tell fx of 0, 0 is 0. That's not how it works. So you have
we
to
can
check.
do like y is equal to x, we can put that, and y is equal to x square, and these like 2-3 conditions we can check and find limit does not exist.
No. You can use two curves to show that the limit does not exist. Not to show that the limit exists, because there are you have to go along infinitely many curves.
No, for not existing.
Ma'am, if limit doesn't exist, then partial derivative also doesn't exist, no?
No, limit of what? Here, no
if limit of
asked,
function doesn't exist, then partial derivative also doesn't exist.
It is not guaranteed.
No, that's not guaranteed. Means it doesn't work that way. Okay, so
limit 0, 0.
Limit at 0, 0.
If limit at 0, 0 not defined, so that is means partial derivative not possible.
No. See, the limit at 0, 0. What is the limit at 0, 0 for this function?
0.
No, put y is equal to mx. The limit does not exist, right?
Does not exist.
Yeah.
Okay, yes.
The limit does not exist, but see, the answer says fy exists at the origin. So partial derivative is actually here. The partial derivative of x exists everywhere. So it actually exists, even though the limit does not exist.
Okay.
The directional derivative at the origin along the direction of the unit vector does not exist. Okay. So
can we discuss this question? Can we solve this question and see like how this works?
Yeah, I'll just solve it for the last option.
Yeah, sure.
Okay, so the function is xy by x squared plus y squared when x comma y is non-zero. And along the direction 1 by root 2, 1 by root 2, and at the point 0, 0. This is the direction. Okay, so how will we find the directional derivative?
Limit f of
1 by root.
Okay.
Limit h goes to 0, f of
0 comma 0.
0 plus h by root 2.
Okay, h by root 2 comma 0 plus h by root 2 minus f of 0 comma 0 by h.
Yeah. So limit h goes to 0. F of h by root 2, h by root 2. So h by root 2 to h by root 2 by that h I'll keep, this one I'll keep it as it is, and then we have h squared by 2 plus h squared by 2. F of 0, 0 is 0. So fine. So this is limit h goes to 0, h squared by 2 by h into h squared.
Yes.
So this limit does not exist, right?
Yes.
Yes.
If 0 comes here, if 0 comes here, if only h will be there and 0 comes.
Where h is there?
If in case 0 comes as the output,
then it exists, no? And the directional derivative at the point 0, 0 is 0 if the answer is 0.
Okay. So in case of 0 by 0 format or 1 by 0 comes, then limit does not exist.
Yeah, 0 by 0 format I'm not telling, because if it's 0 by 0 format, this is one variable limit. Now you can apply L-Hospital rule, right? If you get 0 by 0 format.
Yes.
Yeah. Then you have to check whether at the next stage you're getting an answer or you're still getting it does not exist. That you have to check.
We can use a hospital's rule because it turns into a single variable, right? That is h.
This is a single variable limit. This is not multivariable.
Then we can use a L'Hopital's rule.
Yeah.
Ma'am, here h squared by 2. That how did you get h into?
I just substituted this here at the function.
Ma'am, can you please check partial derivative?
Yeah, I'll do that. So this is I'm using this definition to calculate.
Okay.
So how will we calculate fx at 0, 0?
Quotient rule.
Limit h tends to 0, f of 0 plus h into 1 plus 0, 1 comma 0
minus f of 0
of 0, 0.
by h.
The 0, right? F of h comma 0.
Yes.
So that is 0. X, y is there.
Yes.
So that's 0.
H into 0.
Yeah. Similarly, fy at 0, 0 will also be 0.
Ma'am, there is a doubt. In the directional derivative, we talk about the direction. In some of the question I've seen, they have written like in the degrees, like direction in the degrees. Like I really get confused in that. Like suppose direction 30 degrees from the x-axis, positive x-axis. So can you just
so what is this vector? If it is 30 degree, what is this vector?
Norm of this vector is 1. We have to find the x and y. When we get x and y, we get the point.
No. What is this direction? What is this vector? If this is 30 degree, what is this?
Cos 30 sin
Cos 30 sin 30.
Cos 30 sin 30.
Cos 30 sin 30.
That's all.
Okay. And that's all. Okay.
Yeah.
I was telling him in detail that the norm of this vector is 1, and you can use trigonometry to find that point using sine and cos.
Yeah.
Equate them to x and y coordinates. When you get the x and y coordinates, you get y and x. Then you get the point. Turn it into a unit vector. Again,
you use right angles. That's it. Okay.
Got it.
Madam, on limits, I have a question.
Yeah.
If the function is continuous and the value everywhere, whichever way you approach is 0, the function is still continuous, right?
I mean to say, like in the previous problem, we are having xy by x square plus y square. Instead of that, some function which actually, if I approach to 0, it comes to 0.
Okay.
So
if limit f of x comma y as 0, 0 is equal to 0, then this function would have been continuous.
Okay.
Yeah, but here the limit does not exist.
Okay.
Here it does not exist, but if it was equal to 0, yes, it would have been continuous.
Okay, done. Thank you.
Okay. I guess we'll proceed to week 10. In week 10, the direction of steepest ascent or descent. What is that? What is the direction along which we have maximum rate of change?
Gradient
divided by
gradient.
Direction.
Gradient at that point divided by its norm.
Along the gradient vector, right? At that point. Yeah, if we treat it as a direction, so obviously we want it to be the unit vector. So the maximum rate of change is along the direction of the gradient, and the minimum is along the opposite direction.
Negative of this one.
Negative of this.
Yeah, so you just calculate the gradient, and whatever is the gradient you get, you take the direction along that. That is, you find the unit vector. That will be the direction of maximum rate of change.
Ma'am, one question in this topic. The mock for end-term exam, the explanation is given for the last but second, I guess, question.
Okay.
Mock for end-term question.
That is maximum rate of change.
Maximum rate of change. That is not this concept.
That is norm of gradient. Maximum rate of
so
change.
This is the direction along which it changes, and the maximum. Oh, okay. This is along this direction, and the maximum value.
Vector.
Yeah, the maximum value, the maximum change is this.
Maximum change is the norm itself.
Yeah, and the minimum is minus of this.
Okay.
Yeah, this is the maximum change. This is rate of change along the direction. This is the direction. The direction along which it changes the maximum is the gradient. Direction along the gradient, and the maximum changes the norm of the gradient.
Hello, ma'am. For minimum direction, do you need minus sign? Because in minima, when you write minimum formula, there have already minus sign.
No, the direction will be in the opposite direction of gradient. So y minus sign is the opposite direction. Direction opposite to gradient. So if this is the gradient vector, this is going to be the direction of minimum change, the opposite direction.
But
could you work out that
value into the gradient, that will be give positive.
What is it? Can you please repeat?
When you put these directions into the gradient, for gradient, then that will be give positives. Negative into negative positive.
No, why is it negative? This is going to be some number. It means it's a vector. It may have positive components, it may have negative components, it doesn't matter.
Yeah.
Let's take this function. Say f of x comma y is x minus y.
Extra negative.
What is the gradient of this function?
Yes.
1 minus
1 comma minus
1 comma minus 1, yes.
Yeah, and the maximum rate of change occurs along what direction?
In the same direction. In the same direction.
This direction.
We take the norm of it.
Yes.
And where does the minimum, along what direction the minimum rate of change occurs?
Minus of this.
Minus 1 by root 2 by 1 by root.
Yeah.
And what is the maximum change?
That's norm of root 2, right?
Root 2.
Directly. Okay.
Yeah. And the minimum change is minus root. Means the minimum is minus of that.
Yeah. Here you have taken the gradient.
Okay.
Yeah.
It is just the coefficient of the x and y. That is what it is.
No, it's fx and fy. This is gradient. Okay. And then we have tangents. Okay, fine. So how do we find what is the equation of tangent line and tangent plane? We'll just write it down, write down the formula so that
Actually, it would be better if we write it in a symmetric form. All the other definitions are derived from it.
Yeah, it's easy in the symmetric form. It looks good, but then knowing it in the other two forms makes it easier for more than two variables.
Yes,
in
other
two variables
can be derived from the symmetric equation.
Okay, fine.
Ma'am, I have actually in previous question, f of xy is x minus y. If it is some other function where del f of x is in terms of x and y, then how to find this?
Then you will evaluate at that point. No, I chose it this way so that you will get a number directly. If you should evaluate at the point, right?
Okay.
Say you have 2x, you will have you'll be given a point at which you have to evaluate.
Okay, ma'am. Thank you.
Yeah. What is the equation of the tangent plane? Okay, let's
in the previous example, minimum is minus 1 by root 2, comma 1 by root 2, right?
The direction of change, yeah. Minimum change is this direction.
Oh.
Yeah. Okay, what is the equation of the tangent line? So how do we find the tangent line? Yeah, you'll be given a function at the point something along the direction something. So let's call it a comma b. Along the direction, say u1 comma u2. Then how do we find the tangent line?
X is equal to a plus t u1.
Yeah. So you choose the point corresponding to x coordinate divided by
u1 equal to y minus b by u2 equal to z minus f of ab.
Yeah. So the point for z is f of ab by the gradient, right? The gradient at the point along the direction equal to
t.
Okay. This will be the equation of the tangent line. When you put equal to t, you will get that form, right? The other form, this one, parametric form. This is the equation. When you put equal to t, you will get the parametric form. That's it. So when you put equal to t, you will get x is equal to a plus t u1, y is equal to b plus t u2, z is equal to f of a comma b plus t times gradient of f, the directional derivative of f at ab in the direction of u. If we want to write it as vectors,
xt
that's the vector
equal to
we'll write it as a comma b comma
f of a
comma b
plus
this formula is important.
u1 u2 fu.
Yeah, this formula is important in the sense that if you want to find the tangent line, then this formula is needed. You mean this formula?
Yeah.
No, you can use any one of
these tangent lines. We didn't use in mock or anywhere in term mock, right? That's
no, it was used in mock. That affine space, it used this question.
Okay.
No, that's remember. Tangent plane, not line
tangent
equation.
plane, that is same. Both are same.
Both are not the same.
Yeah,
this is a line, that is a plane, but yeah.
We can derive the line from tangent plane.
Because I use
what is the tangent plane equation?
Z equal
to
f of ab plus.
Because this equation only we used in all everywhere.
Okay, don't blame me if tangent line comes in the exam. I don't remember.
Because it's not in even weekly mock or end term mock, nowhere these tangent line equations
Difficult to
No,
remember, right?
now it is
It's
going
very
to come
easy.
because
Ma'am, this formula is given to in the exam or not? The formula sheet or something
No,
like
no.
stats.
No, we won't give this formula. This is the only thing you have to remember if asked for a tangent line, right?
Ma'am, how to find tangent line?
Okay.
This is the formula. We are not getting into any concept or derivation here. This is the formula. That's it. Any one of these three you can use to find the tangent line. This is the symmetric form, this is the parametric form, and this is the vector form.
Ma'am, in tangent line, z equals to f of a comma b plus t times fu of a comma b. Knowing that is enough, no? That z equals
tangent line means you have to write all the three down. That is when you get a line, right?
So we need to mug up this formula if the question will come.
Yeah, it's easy to remember. So you'll be given a point, you have to associate the x coordinate with x, y coordinate with y, and then the z coordinate will be value of the function at that point. And then the direction, x coordinate of the direction and y coordinate of the direction and the directional derivative at that point. That's it.
Okay.
Ma'am, I seem to have forgotten completely about tangent line. Over here with the third formula, I can get the equation of the tangent line if I know t. So will we be given t?
No. You won't know t.
T is a
This is the line,
parameter.
no. Yeah, because of t only this line will vary. Otherwise, it will be a single point, right? If there is no t, this is going to be a single point, right?
So the equation will have the t.
See, y is equal to say a plus tx or something like this. Okay, fine.
X equal to a plus 2t, y equal to like that it will come. X equal to 1 plus 2t.
As an, yeah. So that t is what is actually making you move along this line.
I think I'll have to practice. Okay.
Fu of AB is the directional derivative, madam, or what is that?
Yeah. The directional derivative along this direction at the point AB. Okay.
When you say Fu of AB, is it like AB projected onto U?
No. This is the directional derivative.
Okay.
Directional derivative of the function at a point in this direction.
Okay.
See, if we are talking about projections, it could have been P or projection. F here denotes the function. So there it will be the directional derivative.
Okay. Ma'am, could you briefly discuss the properties of projections?
It was very clearly explained in the previous session.
Okay.
Maybe you can just watch that.
Okay,
yeah.
sure.
It was explained in detail actually. Okay, and then what is the critical point of a function?
In the definition of critical points, do points where the limit does not exist include?
Yeah, the partial derivatives where they don't exist. The gradient does not exist or the gradient equal to 0. All these points are critical points. You equate all the partial derivatives to 0 and find those points where all the partial derivatives are 0. Those are critical points. And points where the partial derivatives do not exist are also critical points.
Sometimes in some questions, the question discussed in the lecture, sir also took the boundary points. So when do we have to consider these boundary points?
Boundary points for critical points, is it?
Yes, sir. For finding the global maxima and minima.
That is when we want to find the absolute maxima and minima. The critical points, boundary points won't come under the critical points category. When you want to find the global maxima minima, that is when you consider the end points.
Okay.
Yeah. So in all our functions, mostly, 99% all functions are continuous and all that. So no problem of this, means this case mostly doesn't arise. So what we just do is Find out all the partial derivatives, put it equal to 0 and solve whatever points we are getting. Those are critical points. And how will we check whether it is maxima or minima?
Second
derivative. Function value at that point.
We don't have second derivative here. Means it's all Hessian derivative, right?
Hessian derivative.
Hessian matrix.
Yeah. So you will find the partial derivatives, the second order partial derivatives, the mixed partial derivatives and all that. And the mixed partial derivatives will be equal if the partial derivatives are continuous and all that, right? The Clairaut's theorem. But all our functions are nice, so no problem. So how is the Hessian matrix defined?
fxy, fyx,
fyy.
No,
fyx.
Yeah, fyy.
This is correct? Or it's
Yes.
No, ma'am.
Yes, it's correct.
fxy.
Yes.
No, ma'am, it's correct.
No, ma'am.
Okay.
It is not. F of fx, then it should be fxy.
No.
Differentiate.
You take the vector, you take the gradient.
Okay. First of all, write the fx and fy. We take first component. Ma'am, see, we take first component of the gradient. Then in the first of Hessian matrix, it comes its derivative with respect to x. Then its derivative with respect to y. In the second row, we take the second component of the.
Right. So this is right?
Yes, ma'am.
Yes, ma'am. Right.
Yeah.
Now, as per the matrix, XX, XY only.
Yes, ma'am.
Yes, ma'am. It should be
and
fxy.
No, I don't feel
No,
it
ma'am,
is.
you're right.
No, this is correct. This is correct.
Yes.
You take the gradient vector and then differentiate it with respect to x. That will be your first row. You take the gradient vector, differentiate it with respect to y. That will be the second row.
Actually, in the video, sir, because of the Clairaut's theorem, did not bother about the order.
Actually,
and
we
that's why
didn't
he wrote
bother.
that.
Yeah.
Yes.
Yeah, so that's why there's this confusion.
So because of the
Actually, it
Clairaut's
should be-
theorem, most of our functions are nice. So these two will be equal. So it doesn't matter where you put what.
Actually, the notation fxy means that the differentiation derivative of fx with respect to y.
Yeah. Okay.
So that is why in the first row we write fxy.
No, this is exactly why you should put fyx in the first row, right? The gradient vector with respect to x, you differentiate. So fx with respect to x, fy with respect to x. That will be your first row. Okay, anyway, currently it doesn't matter. Okay, so this is the Hessian matrix. What do you do with the Hessian matrix? When do you tell it is a local maxima, local minima, or a saddle point?
First, if determinant is positive.
If the determinant is less than 0, it is the saddle point. If determinant is greater than 0, only then we have to check whether it is maxima or minima.
That is
Then what do we do?
That is given by the fxx.
fxx is
Less than 0, then it is maxima.
Yeah.
Minimum.
And when is the test inconclusive?
Equals to
When
0.
it is equal to 0. Determinant is 0.
Yeah. So this is the conditions for testing whether a two-variable function is having a point of maxima, minima, and all that. 3 variables. When we have 3 variable functions, then we'll have a 3 cross 3 Hessian matrix.
Yeah.
3 cross 3 determinant.
Yeah.
Ma'am, for minima, it should be less than 0.
Actually, sir defined the 3
Minima
cross
to be
3, 2
greater than
cross
0.
Minima greater.
Maximum.
Determinant is greater than 0.
Maxima is less than 0.
And sir defined three of these: 3 cross 3, 2 cross 2, and 1 cross 1.
And 1 cross 1.
Plus gives us minima.
All positive gives minimum.
And minus plus minus gives us
negative gives us maximum.
If these two are
point
not,
is easy.
Yes. 2 cross 2 is always
then determinant is
saddle
zero.
point is also not easy in this case. Inconclusive is easy. Determinant is 0. Okay.
Less than 0.
So for maxima, this should be less than 0. This determinant should be greater than 0. fxx, fyy minus fxy squared greater than 0. And the determinant should be less than 0. For minima, everything should be less than 0. Greater than 0.
Yeah.
Minus fxy squared greater than 0. And the determinant is also greater than 0. For saddle point, if either of this doesn't happen, determinant is non-zero and not maxima or minima. Then this is the case. These are the conditions.
Saddle point.
Ma'am, if xx, if yy minus if xy whole square is less than 0, then it's a saddle point, right?
Yeah, if any one of these, if these two cases don't happen, then it is a saddle point. So if this is less than 0, even that comes under saddle point.
Okay.
Okay, so this was and differentiability.
One more thing that for both minimum and maximum, that fy and ffx, you can show that phase. For maximum minima, this is same.
Yeah. These
Right.
two will be of opposite signs. Plus, no, what? Minus, plus, minus, plus, plus, plus. And then the last lecture was that differentiability and just that one limit. You know, this limit should exist, then it is differentiable. But yeah, since not much has been discussed about this, you can ignore this. But you need to know what differentiability is, so it has been included. Okay, someone had asked about some mock question, right?
Ma'am, can you explain direct assignment question 9 from solution? Can you open the solution?
Affine mapping.
Yeah, I'll do affine mapping. Which week graded assignment?
11.
Okay. Okay.
Then can you open the solution so that it is easy to, I have a confusion.
Okay. Have I done something wrong in the solution?
Ma'am, 9th question.
That partial derivative question, what I asked, that is also solution is incorrect. Question number 4, partial derivative. A partial derivatives question number 4 we discussed, right? Limit doesn't exist. Solution is wrong for that also. Weekly
that was mock, right?
Weekly
yeah,
mock. Question number 4. Solution was wrong.
What have been? Okay, fine. Yeah. Question number 9. Yes.
Yeah, here, ma'am, can you explain fx? Actually, I missed the sandwich theorem. So how to whenever x minus y square, x minus y to whole square, it just take the right side. And then fx 0, 0, if you find the limit.
This has nothing to do with x minus y squared. This has things to do with sign. Sign is less than or equal to 1, greater than or equal to minus 1. That is what happens here. Sign of any value.
Yes.
Sign function lies between minus 1 and 1. No, that is what is written here.
Suppose we don't use sandwich theorem here. See the first line of the solution. You have written limit x comma y goes to 0, 0, x minus y square, all that. Sign function varies from minus 1 to 1, right?
Yeah.
then x minus y square goes to 0. 0 multiplied by the sine function, it goes to 0. So why do we need the sandwich theorem here?
No, when you put 0, 0, this is becoming 0, 0, right? 1 by 0. No, that is why you want to do something more. You have a 1 by 0. That is why you're trying to do something else. See, whatever you said, no, sine function lies between -1 and 1.
Yes.
That is correct, but you're implicitly applying sandwich theorem. That is why this is happening. That is why whatever you said is happening.
Ma'am, in the fx, we find the 0, 0, limit s tends to 0. If we find that one, I solve this, we find h square sine 1 upon h upon h.
H squared sine,
So we solving this, we find sine 1 upon h upon 1 upon h. It should be 1, so
no, h goes 0, no? So 1 by h goes to infinity. So in that case, again, you'll be using sandwich theorem there, right?
Ma'am, here we apply the
sine 0 by 0.
Sine x
by x as x tends to 0.
As theta goes to 0.
Theta goes to 0. X minus y will be equal to 0. So one pair will remain.
This is what we have. Or the other way around. Theta goes to infinity. This is what we are using.
Okay.
You have 1 by h, right? So h goes to 0 means 1 by h goes to infinity.
Infinity, yes, ma'am.
Hello.
Yeah.
Hello. Ma'am,
Yes.
I have a doubt in solve this question number 8.
Week 11, is it?
Yes, ma'am, week 11.
Okay. What is the doubt?
And here in this question, I cannot understand how find its local minima or maxima because we have no.
Did you find the Hessian matrix?
Yes, ma'am. I have found Hessian matrix.
Okay, then why aren't you not able to classify? The conditions are clear, no? Here we have these conditions.
Yes, ma'am.
Did you do this?
Ma'am, I do this after doing equation sum in x or y.
No, you have to substitute at that point. No, whatever is that critical point, you have to substitute that. Then you will have only numbers.
Okay.
So when you find the Hessian matrix, this matrix at that point you have to do whatever at that critical point. Okay, any other doubts?
Ma'am, same here. How to find the differentiability? I'm stuck. Ma'am, 11.
So for differentiability,
graded 11.
Oh, of that question, is it?
Yes.
So did you check the solution? Did you understand the solution?
Yes, ma'am. You leave it where I'm got stuck.
And that's again the sandwich theorem, right?
Yes, ma'am.
It's the same limit, I think. That's why I had left it off there.
Ma'am, 9.
Yeah.
Yes.
So you're getting the same limit, right? Same as what we.
Okay.
So for this, it will go to 0. So yeah.
Oh.
Ma'am, here sine of h like 1 by x minus y, but we put in the sandwich theorem that x minus y whole square. So will it not be 1 by x minus y to whole square?
Where?
This question only, ma'am. Here that sandwich theorem is there, no? So instead of that is signed 1 by x by y, right? So we will put that x by minus 1 and plus 1 limit. So that will be x minus y whole square, or it will be 1 by x minus y whole square.
No. See, you have x minus y whole squared sine 1 by x minus y. We know sine 1 by x minus y is less than or equal to 1 and greater than or equal to minus 1. So I will just replace this. So x minus y whole squared sine 1 by x minus y is less than or equal to x minus y whole squared into 1. And this is greater than or equal to x minus y whole squared into minus 1.
Okay, ma'am. Got it, ma'am.
Ma'am, I have a small doubt. So,
Okay.
ma'am, when we have for differentiability, we have limit formula as well as the sandwich theorem, we can find the differentiability. So, when we should use that limit formula to find differentiability and sandwich theorem to use to find differentiability?
No. To find to check whether it is differentiable or not, you have to evaluate this limit. To evaluate limits, there are multiple ways of evaluating limit, right? You choose the one that is easiest.
Oh.
So because to evaluate this limit, I'm using the sandwich theorem. Means I can squeeze this and find the limit easily. That is why.
So how can we identify that, ma'am? By seeing some people can identify that we can do this using a sandwich theorem.
It comes out of practice actually. See here, it's not easy to, when h comma k goes to 0, 0, it is all filled with zeros. So it's not going to work that way. I cannot substitute and do things. But whenever I have sine and cos, one thing I can do is that I can always use that less than or equal to 1 and greater than or equal to minus 1, right?
Ma'am, will the sandwich theorem hold for everything? So every function.
Sandwich theorem holds even in multivariable case.
Okay, if the left hand side comes with 0, if we multiply some number with 0, it will be remaining 0 only. So will that not be?
Yeah.
Okay, ma'am. Thank you, ma'am.
That is actually why we are getting this limit to be equal to 0.
Okay. Thank you.
Ma'am, in solution of week mock for week 9 and 10, in question number 4, it is given that directional derivative is existing.
It is wrong. It is wrong.
Ma'am, solution is wrong or?
It does not exist.
Why, ma'am?
We did that problem, no?
Means if limit doesn't exist of the function, then directional derivative also doesn't exist.
Yeah, the directional derivative is nothing but that limit, right? So if the limit does not exist, then actually the directional derivative does not exist. That is what is the definition of the directional derivative, right?
Okay. If मतलब अगर limit नहीं है, मतलब directional derivative भी नहीं होगा.
Yeah, because the directional derivative is nothing but that limit.
Okay.
Okay. And then maybe let's quickly discuss.
Ma'am, I had a doubt related to Clairaut's theorem. Can I ask?
Yeah, what is it?
Ma'am, where will we use that or where will we get satisfied? I'm confused with that.
So for this course's point of view, Clairaut's theorem will be satisfied by all functions. So you have to check whether the partial derivatives are continuous at that point.
Because we are using Hessian matrix, and whenever we use Hessian matrix, it will be satisfied. Is it like that?
Because all our functions are nice. They are all continuous and all partial derivatives are also continuous.
Okay. And whenever it will be continuous, it will be get satisfied, right? In open bound.
Yeah. So whichever partial derivatives you are considering, those two partial derivatives should be continuous.
Okay. So it will be satisfied in all the cases in this course, right?
Yeah.
Thank you.
Hello, ma'am.
Yeah.
For differentiability, how do I check?
You have to evaluate that limit, that big limit.
Yes. But in one variable, we done by partial derivative, not partial by derivative. But
yeah, because in one variable you have only one derivative. Here you have multiple things.
So I need to, first of all, I need to find a limit. So
that big limit, yeah, h comma k goes to 0, 0, that limit.
Okay, if limit is exist, then
the function is differentiable. If it does not exist, it is not differentiable.
Okay.
If it exists, it will always be 0. So if it exists, means if the limit is 0, then the function is differentiable. If the limit does not exist, then it is not differentiable.
If it is not equals to 0, that is mean
No,
that is not
if it
differentiable.
exists, it will be 0.
Okay.
Yeah.
One thing. Okay.
Madam, one doubt in graded assignment, week 10, question number 2.
Okay.
Last two options, madam. Maximum occurs 5, 5. I'm able to calculate at 5, 5, but how did we arrive at 1 root 3 to say like that could be maximum? Like where does the number come from?
Which one? Option 3, is it?
Yeah.
No, I think the maximum occurs in any direction along.
That is
means 1, 1. Yeah.
That is it, madam. Like. Okay. And
I don't know. I don't remember the solution. I have to solve and check. Did you check the solution? Is it clear there? Why?
Yeah, the directional vector 1 root 3 is given, and the direction is also given. Like it is stuck whether it came randomly or because it's by definition we go by it is the maximum gradient occurs along the direction. Therefore, we took that value. I was not able to kind of understand that.
Let's check.
Solution is given such. And also the fourth option, somehow, you could explain it a bit, it will be helpful.
There's no plane which contains all the...
That option I too didn't understood. Option 4.
There's no plane which contains all the tangent lines at 0, 0, and hence the tangent plane does not exist. So you just have to check the thing. If the partial derivatives don't exist, then the tangent plane will not exist, right?
Okay. Okay, that's how we conclude that.
Could you please repeat?
If the partial derivatives don't exist, then the tangent plane also won't exist, right?
Yes. Okay.
Madam, in general, for sandwich theorem, like sine and cos is okay, but if something else, would we be expecting some other kind of function like tan?
No. In this course, definitely not.
Definitely not. So basically, if the sine or cos comes, we have to check for -1, 1, and 3 how it goes from there. Thank you.
This 5, 5, that's a random direction that's given. You already know that the maximum is along this direction. So you find the gradient and then you get this 1, root 3. So that is the maximum change possible, right? Means along that direction, you will have maximum change. So along 5, 5, that's not possible.
So 5, 5 is like a random number. Like we just have to see.
Yeah. The option is not true. So it's just a random number.
Okay. As long as it is not in the direction of gradient, we can just simply say it's not.
Yeah.
Not. Thank you.
Okay. I guess we'll quickly define what an affine map is. So what is an affine map?
Moving a vector space with a vector.
Please एक दो example बनवा देना ना affine map का.
Then I will just go with that week 7 reflect with us problem that has everything.
Yes, ma'am.
Did you watch that live session in which
Yes,
I
explained
this? Yeah, then what is the doubt?
मैम
Did you
एक दो
understand
क्वेश्चन है जो नहीं बन पा रहे मींस जैसे जो पिछले टर्म के जो एंड टर्म में एग्जाम में आया था वो लाइक अफाइन मैप को प्रॉब्लम नहीं बन पा रहा था.
Okay, can you tell me that question? I will solve that then.
Madam, I have doubt question.
Is it regarding affine map?
Yeah, last terms.
Yes,
paper.
So मैम कहाँ से भेजूं मैम मैं आपको?
No, you just read it out. I'll write it.
मैम वो 2-3 क्वेश्चन सब साथ में मिला के.
No, okay, 1 second. Are you sure it's last terms?
Yes, ma'am.
Could you check in video?
Is it the same question in which it is a 2 cross 2 matrix is given?
I think so. That's what I remember.
Ma'am,
Yeah.
last question, max to last question, previous term.
Yeah, just
April 3, April 4 को पेपर हुआ था।
वहाँ पे 2 cross 2 मैट्रिक्स दिया हुआ है क्या? 0 1 1 0 something like that.
is it this question? Is my screen visible?
Yes, ma'am.
Yes, ma'am.
Yes.
Okay. So what is happening here? We are given a function, tangent plane, okay, vector space, and then affine space, and all that is done. Equation of tangent line, direction derivative, okay, something and all is happening, and then we have arrived at basis and all that. Okay, let T denote the linear transformation from V1 to V2 whose matrix representation with respect to the ordered basis beta and gamma. Okay, beta is found, gamma is found. Okay, and the matrix is given. Okay, fine. So what is given? T of -1 0 -3, -1 0 -3, T of 0 1 3, T of 0 1 3. This is equal to, it is the identity matrix, so simple, 1 0 1 1 0 -1 0 1. Is it clear that these are the images?
Yes.
Because the matrix is identity matrix, right?
Yes, ma'am.
So is it clear that this is T? And we already know T completely because V1 is two-dimensional, I guess. Let V1 denote the corresponding vector space associated with, okay, x minus y plus z is equal to 0. V1 is x. Oh, this is A2. What is V1 then? Okay, let's generate it from the basis then.
Even
V1 is
we have to
alpha times -1 0 -3 plus beta times 0 1 3. So this is
minus alpha. Minus alpha.
I think it is x plus y minus 3z is equal to 0, right? This is what? This can be written as plus plus. So whatever is the value of z, that is 3 times the value of x. Right. This is correct, right?
मैम ऐसे पॉजिटिव कर सकते हैं क्या?
Span is the same, no? Span of the negative vector or the positive vector is the same, right? Span of 1 0 0 is same as span of -1 0 0, right? So this is my V1. What should we do? Which of the following functions denotes an affine mapping from A1 to A2? Okay, fine. Okay, what is A1? Did you calculate A1? What is that number that we are getting? Has anyone calculated A1? Some number we'll get here. Let's check what that number has to be. Z minus 4. So I think it should be 4. I don't.
He is not given here, madam.
What is not given?
points are not given.
No, but
We have
A1, when
to
you
see.
calculate A1, you would have got some number. So when you calculate like A2 is x minus y plus z is equal to 1, no? Like that you would have got some number for A1.
How do we get A1?
A1 is this affine, the tangent plane of this function at this point.
Okay.
I think we'll quickly do that. X squared y plus xy squared. Two x y plus y squared, comma x squared plus 2xy. And what is the point? The tangent plane of the function at the point 1, 1. So that's 2 plus 1, 3, comma 3. So z is equal to f of a comma b. 2 plus fx of a comma b into x minus a plus fy of a comma b into y minus b. So z is equal to 2 plus 3x minus 3 plus 3y minus. So 3x plus 3y minus z is equal to 6, 2. Okay, it's 3x plus 3y minus z is equal to 4. Okay, so now we have to find the affine mapping. First of all, for the affine mapping, f is defined from A1 to A2. So f of x, y, z, these should be points of A1, right?
Yes.
Yeah. So first of all, okay, fine. Let's ignore that. Let's go to the right hand side. So I want points in A2. That is, I want points satisfying that x minus y plus z is equal to 1. X minus y plus z is equal. I want points satisfying this. Or I think from the linear transformation we will do. So from here, let's find out the linear transformation. Alpha times minus 1, 0, minus 3 plus beta times 0, 1, 3. Okay, so first I need to express points in the vector space V1 in terms of these two vectors. So how is the vector in V1 going to look like? X comma y comma oh, so this is also different. X comma y comma 3x comma 3, 3x plus 3. This is correct, right? Do you agree to this? Because V1 is 3x plus 3y minus z is equal to 0. So this is clear, right?
Yes.
Yeah. I need to express this in terms of these two vectors. So alpha times minus 1, 0, minus 3 plus beta times 0.
Linear transformation you can get from x, y, z equal to what?
Hello.
I think she disconnected.
Can someone please tell which question is this? Is this the mock?
Previous term and term.
Previous term. Okay, thanks.
I think this is the question explained in the video link sent by
No,
Subhash.
no,
Subhash.
no.
Not that different.
No.
Different type of question.
Where is this available?
Announcement link. You can see it.
Where previous term questions are available.
Yeah.
Can't we check the answers, options? Can't we cross check with the options like basis for this question? Did you try?
No.
Okay.
Hello. Can you share the link where the previous questions are available, please?
I'm also searching. If someone can share, that would be great.
भेज दिया, चेक कर लो.
Yeah, thank you.
इस टर्म में अफाइन मैपिंग किसी ने समझाया है क्या अच्छे से?
हाँ, सुभाजीत सर का सेशन है.
कौन से सेशन में? आप सेशन का लिंक भेज देंगे क्या?
The link is available in announcement section.
लिंक एक्चुअली शिवाजीत सर ही भेजे हुए थे अनाउंसमेंट में, तो उसमें आप वीक 7 में जाओगे तो मिल जाएगा. नहीं एक्चुअली वीक 10 में भी वो डिस्कस किए हुए थोड़ा सा.
नहीं, वो जो मेल में भेजा लिंक में कुछ समझ में नहीं आ रहा है.
वहाँ कुछ समझ में नहीं आ रहा है.
नहीं यार, वो कुछ नहीं समझ में नहीं आया मुझे भी. वो
अच्छा मैम तो आप तो मैम हाँ, ये थोड़ा डिफिकल्ट है अभी. तो आप ये कर सकते हैं कि एक पिछले टर्म का आप वो देख सकती है, रिवीजन सेशन देख सकती हैं 7 to 9. तो उसमें आई थिंक लिटिल बेटर है. और बाकी तो ये टॉपिक ही डिफिकल्ट है, तो हाँ आई वुड से कि थोड़ा डिफिकल्टी आएगी समझने.
नहीं, थोड़ा बहुत समझ आ जा रहा है. 1-2 एग्जांपल्स बना के दिखा ले तो समझ आ जाएगा.
एक्चुअली अफाइन मैप का प्रॉब्लम ये पर्टिकुलरली होता नहीं है, मेनली तो ट्रांसफॉर्मेशन ही होता है. अफाइन मैप तो वहीं तक है, बस जो एडिंग चलता है बस वहीं तक है. उसमें
पिछले साल का आया हुआ है करके मैं बोला एक बार पूछ लेता हूँ, क्योंकि इम्पोर्टेंट हो सकते हैं पिछले टर्म में आए हुए.
इम्पोर्टेंट तो है ही, हर टर्म में ही आया हुआ है एक्चुअली, नॉट इन ओनली इन टर्म, सब टर्म में आया हुआ है. और आई थिंक कि पिछले वाले क्विज में भी आया हुआ था एक क्वेश्चन इससे.
किस्मत अच्छी हो तो सब स्पेस आ जाए तो ज्यादा अच्छा है.
इम्पोर्टेंट है, बट मेनली इसमें ट्रांसफॉर्मेशन का यूज है. मतलब अफाइन मैपिंग ऐसा कुछ खास
एक्चुअली इतना टाइम भी नहीं
तो
मिलता है ना सब क्वेश्चन सॉल्व करने का, तो एक दो तो छोड़ना ही पड़ेगा.
तो मैम एक वीक 6 का 6th प्रॉब्लम है, वो वाला ट्रांसफॉर्मेशन वाला, तो वो आप कर लेंगे तो आई थिंक रिलेट कर पाएंगे इससे. वीक 7 का ये रिफ्लेक्ट विद अस से, तो उसको एक बार आप देख लीजिएगा. वीक 6 का 6th
अरे रिफ्लेक्ट विद अस वाले का अगर कोई मेरे को नॉर्मली मेरे को आखिरी स्टेप तक समझ आ चुका है, उसके बाद का बस थोड़ा सा बच गया.
यार इधर एक दो तमिल लोग भी है, and we find it difficult when you guys discuss with yourselves in Hindi. If you guys can translate. हाँ
yeah we can, but we are discussing only those topics which are
नहीं
not
मुझे हिंदी आती है, मुझे कोई दिक्कत नहीं.
अच्छा yeah I can understand, but he wants to speak in English, so it's I think it's okay.
Which question in week 6? Which question in week 6?
Practice assignment.
I think practice
assignment question.
6. I think question 6. Yeah.
Question
Ma'am,
6 in week 6. Okay.
Yeah.
That will
Right.
help in understanding even that affine mapping.
नहीं वो हेल्प नहीं करेगा मैम एक्चुअली वो है कि मतलब उसका वो ऐसे ट्रांसफॉर्मेशन का यूज है अफाइन मैपिंग सो या इट विल हेल्प नॉट इन अंडरस्टैंडिंग एक्चुअली इट इन सॉल्विंग
भाई अगर कोई
Quiz 2
affine
one question
mapping
is there, not that much only we can solve the affine space related.
हाँ मे बी यस
भाई
वो
आपको
solve
समझ आ
कर
गया
सकते
क्या?
हैं अभी।
हाँ मुझे
Quiz
तो
2 में
समझ
एक
में आ गया
question ले।
भाई
मुझे तो
समझा
समझ
दोगे क्या?
Am I audible?
Yes, you are audible.
Sorry, I lost connection.
No problem ma'am you can continue.
Yeah, I'll just wait for them to make me co-host. Oh, I'm already co-host. Oh, the other account has not been seen. Okay, fine. I have to wait then.
For this question, can't we cross-check with the multiple options?
Yeah, we'll do that also.
Yeah,
Yes,
that's
ma'am.
better than solving.
That's better, ma'am.
No, but you know, how will you cross out? For that you need some.
That's what. Yeah.
I had actually called Shubham to ask him to join, and I guess he has also joined. Just give me a moment. हेलो शुभम मैंने ज्वाइन कर लिया हाँ ठीक है okay till they make me co-host can we discuss any other questions or even then I cannot share okay. Yeah you can till whatever we discussed till now with respect to that question it's clear right why we were taking that basis and all that. Am I audible?
Yes ma'am. Yes ma'am you are. Yeah it's clear.
That part is clear, but how to get the linear transformation?
Hello, ma'am.
That part we need.
Yeah, we'll do that.
So, ma'am, any final tips for the exam?
1 second. Hello. In a co-host ஆக்குறீங்களா எனக்கு network disconnection. Okay. Yeah. What was it?
Any final tips for the exam?
One thing is you should recall all concepts, whatever you're thorough in. And one more thing is you shouldn't leave any concept. Means even if you're not very thorough with respect to certain concepts, it's okay, but you shouldn't leave any concepts. At least the formulas, it's better if you know, because what if a problem starts with a concept you didn't study, and then the problems that it follows with other things. So you should know at least the formulas of everything.
Ma'am, here in mock, actually, for checking inner product, there will be 4 rules, ma'am. Even in quiz as well as in mock, they gave that 4 rules, so we can check those rules. So we need to buy heart. Those rules will be given.
Actually, you should. It will be given, but you should know the thing.
Okay.
In the sense that, yeah. But I don't remember, but mostly we'll give it because we have given it for the other exams.
Yeah.
Okay, fine. So is this part clear? How we got this alpha and beta? We started off with the basis. Means this is a vector. Yeah.
Ma'am, can you please scroll up for a minute and
yeah. So ignore this. Ignore this. We had a vector space V1, which was this, and we had a basis for it. Now we are trying to express every element of V1 in terms of the basis vectors. So any element in V1 looks like this because this is my V1. In terms of the basis vector, so alpha times this plus beta times this, we want to find out what is alpha and beta. Clear? Is it clear till this?
Not for me, but I'll watch YouTube.
Hello, ma'am.
Yeah.
Here we can find linear transformation equating right hand side with xyz also. Why we are
Right
not?
hand.
XYZ. You have written
Yeah, we can do it that way also, but this is easier. No, I will have fractions otherwise. Means, are you telling like this? Z minus 3y. Yeah, we can do that also, but it has fractions. No, by this is simpler. Okay, so what is T of this? It's 1, 0, minus 1, and then 0, 1, 1. T of this is 1, 0, minus 1, and this is 0, 1, 1. So my linear transformation is this: minus x, comma, y, comma, x plus y. Fine. So what is my affine transformation going to be? F of x, comma, y, comma, z, whatever, such that x, comma, y, comma, z belongs to A1. What is it going to be? Am I audible?
Yeah.
Yes. Some W plus the transformation.
What is that W? This is my A1. Okay, I want A2. This is my A2.
A1, A2 is known, but point is not.
Point is not given, but it should be a point in A2, right?
What, ma'am?
It should be some point in A2.
Yeah.
Means B, that B has to be. So everywhere there is a 0, 0, 1. That is the point that we have on the right side, right?
Ma'am, we are getting.
So, ma'am, we have to guess the point, or?
But in question it is
No,
not given.
here the point is not given. Yeah, here the point is not given. But
so we have to guess.
Here it is 0, 0, comma. Once I know 0, 0, z coordinate has to be 1 or minus 1. 1, right? It has to be 1, right? If x is 0, y is 0, z has to be 1, right? So if some option had 0, 0, 2, then that would not be a right option.
Here, what's the use with the identity matrix given? Transformation.
That is how we got the linear transformation, right? Because of the identity matrix only we got this linear transformation. Because of that only we got this. Otherwise we wouldn't have known this, right? Just think about it. Otherwise we wouldn't have known that. So this is my linear transformation. This has to be shifted by the point 0, 0, 1. So minus y, minus x, y, x plus y plus 1. So this is the affine mapping. Minus x, y, x plus y plus 1.
Ma'am, you took 0, 0, 1, just anything that satisfied that x minus y plus z is equal to 1.
Yeah. I took it from the options.
Yes, ma'am. So it's not certain. It will depend upon the option.
Yeah.
Whichever will satisfy the equation, that will be correct.
If some point is given, then that's a different thing. But here, since there is no point that is given, it can be any point in A2.
Yeah, correct.
Could you please brief the entire process once?
Y, Z minus 4. How?
That will be a point in A1. That's all. 0, 0, minus 4 will be a point in. What is A? We had A1. No?
Okay.
Here, 0, 0, minus 4 satisfies this. It is a point in A1. That's all.
Ma'am, did we really use A1 here?
Yeah, we did, right? Okay, to get V1.
You please brief the procedure once again.
Yes,
Entire procedure quickly.
So first thing, what you will do is you want to find T. And after you find t, you can write f is equal to some point in A2 plus t of x comma y comma z. So this is all that you want for the last question. But how will you find t? To find t, you don't know t, but you know the matrix of t with respect to some basis. So from the matrix of t and the given basis, we find t. So how did we do that? We know the matrix of t and we have a basis. So express every element of V1 in terms of the basis elements, the given basis. And then after you do this, apply t. And then after you apply t, you get t. So t is known here. So that's what we did here. Express every element of V1 in terms of the basis vectors. And once that is done, you apply the linear transformation. Using the matrix of the linear transformation, we already know the image of this and this. That is this and this. So from there, you get the linear transformation. Once you get the linear transformation, you just have to shift it by using that one vector.
This linear transformation part is not yet clear for me.
Is this clear?
No.
Is this clear? That this is how a point in V1 looks? Yeah.
Yes.
And this is the given basis.
Yes.
So any point in V1 can be written as a linear combination of vectors of the basis, right? Because the basis spans the vector space, right?
Okay.
So I am finding out what is that coefficient here. So any point in V1 can be written as minus x times this vector plus y times this vector. Now I am applying linear transformation.
Okay, understood.
So is this problem clear?
Yes.
Ma'am, could you show A1, please?
Yeah. A1 is this. A1 is the tangent plane corresponding to this function at the point 1, 1. So we quickly calculated the tangent plane here.
Ma'am, we used A1 to find V1?
V1, yeah. A1 is the affine space, so you just have to put that constant to be equal to 0 to get the corresponding vector space, right?
Yeah.
And then we determined the basis for that 3x plus 3y minus z is equal to 0.
That was a previous problem. I used this. I didn't do it there. I used this.
Okay.
So here we didn't use V2 and A2.
V2 and A2 we used here. V2 we didn't use, but A2 we used to get this plus 1. Means suppose this option had plus 2 here, it wouldn't have been a point of A2, right? 0, 0, 2 is not a point of A2, right?
Okay, okay.
Yeah.
Ma'am, formula for affine mapping A1 to A2 say that f v plus v prime is equal to w plus transformation of v prime, where v and w are the point where we are shifting that subspace to that point. So here point is not given. So how this question is like if option is not given here, how
this
can
point is not given, right?
Yeah, yeah.
This I know. Right? T of x comma y comma z we found out, right?
Yeah. Yeah.
Yeah. So this point can be any point in A2, right?
A2.
Means my f is from A1 to A2.
Yeah.
So that f of something should be some point in A2 plus t of x comma y comma z. Means this is that point in V1. F of some V plus
Q.
Let's say W plus V1, where V1 is a point in the vector space V1. This will be equal to some W prime plus
T W.
T of no V1. T of V1.
T of V1. Okay. Subspace is V1. Okay.
Yeah. So this we found out. This is any point in A2. This is any point in A1.
Okay, madam. Now I.
Yeah. Is it clear to everyone? It's a step-by-step process. That is why all these questions are interconnected.
I have a very small doubt and still stuck with that. When you were calculating V1 and you had taken the basis in terms of alpha and beta, that led to x plus y minus 3z is equal to 0. And in that you had taken the negative.
No, here, this is this. Sorry, that was not right. 3x plus 3y minus z is 0. This is V1.
Oh, okay. Okay, got it. Thank you.
What I wrote first was wrong. It's not x plus y minus 3z. That's not it. This is
still, I was trying to understand that only. Okay, so 3x plus 3y, could you please quickly show how from this alpha and beta it had come? Alpha is 1.
Alpha is x minus x. Yeah, here. Alpha minus alpha, comma, beta, comma, 3 alpha plus 3 beta. Or minus 3 alpha plus 3 beta should be equal to this vector.
How did it become 3x? Sorry?
Where?
So minus alpha, how did it become 3x plus beta became 3y?
No, I put z is equal to 3x plus 3y because we are in V1, right? I have only 2 independent variables.
Oh, okay. I'm getting it now. Okay, thanks.
Yeah.
And suppose, madam, suppose we want to find mapping A2 to A1. How do we find here? A1 to A2 is good, but A2 to A1, how do we?
No, then the transformation also would have been from V2 to V1.
V2 to V1. Okay.
No, why do you want to find from A2 to A1? Like, why do you want this?
Such
You
question
want...
I have. Such question. Shivaji sir posted a video of affine mapping, transmitting, where such type of question have been. Find affine mapping from A2 to A1. Question number 6 is that. Find.
Okay, I'm not sure what you're talking about, but that's not needed.
Okay.
I think there is some kind of a misunderstanding. Maybe you should watch that again to see what exactly that is. Okay, any other doubts?
Ma'am, week 7, reflect with us.
Arey, you told you wanted a problem in this and then I did this, right?
मैम उसमें लास्ट स्टेप समझ में नहीं आया रिफ्लेक्ट विद अस में लास्ट स्टेप बस
Exactly same procedure there also. There the point is given. This point is given there. So you just add this point to the transformation.
Okay.
Yeah.
Okay, any other doubts? So here in this question, that point is given. See, it's given that f of u is 2, 0, 1 plus t of u. So all that you have to do is find out t of u. Any other questions?
And we need to know the cos and sine values of common numbers.
Yeah, definitely yes.
Okay, I've been out of school for so long, I'll have to look them up.
Okay.
Hello, ma'am.
Yeah.
I have question mark 5 and 6, madam. Question number 9. Transformation of transformation. Yeah. Question number 9.
So
Mock.
you had asked this in the previous thing
Yeah,
also, right?
previous session, but I didn't get, madam, that time. Solution I have seen. So after T3 same transformation have appeared in that.
Okay.
Yeah, sir, madam. Question
What
number
is
9. Yeah.
yeah, what is T? Did you find out T?
T.
Oh, it's given. Okay, okay. T
Yeah,
of
yeah,
x1, x2, x3 is x2, x3, x1. T of x1, x2, x3 is x2, x3, x1. So what is T squared of x1, x2, x3? How will you find this? T squared can be written as T of T, right?
Yes, yes, madam.
So what is T of x1, x2, x3?
X2, X3, X1. X2, X3, X1.
X3, x1, yeah. Now, what does T do? Whatever is the first coordinate will be sent to the last position. Whatever is the second coordinate will be sent to the first position. Whatever is the third coordinate will be sent to the middle position, right? So what is T of x2, x3, x1? Whatever is the first coordinate will be sent to the last position, right? Whatever is the second coordinate will be sent to the first position.
X3 and then.
Is it clear?
Yeah. Yes.
What is T cube now?
T of X3, X1, X2. Okay.
So what will that be? X3 will go to
Last.
X2, X3, X1. Same.
x1, x2, x3, right?
Yeah. X1, X2. Okay.
So this is the identity transformation, right? x1, x2, x3 goes to x1, x2, x3.
Okay.
So now you need to calculate T4, right? T power 4. Because T power 4 is T of T cube. T cube is identity. T power 4 will be. Yeah. Any other doubts?
TQ is identity. So transformation of identity matrix is equal to T.
T cube is identity means whatever vector you act on T cube will go to the same vector. T cube of x1, x2, x3 will go to x1, x2, x3. That is why it is identity. It is fixing the same, means all vectors are fixed.
So same.
What does the identity matrix do? You multiply any vector with the identity matrix, you get the same vector, right?
Yeah.
So identity transformation means it fixes the same vector. Like that, if a transformation is fixing all vectors, it has to be the identity transformation.
Okay.
Any other doubts?
Ma'am, week 9 practice assignment 9, question number 6. So I just want to understand that particular statement mentioned over here. That is, the limit has been given separately. I'm not sure how to interpret that question. That
So
is
did you
that
check the
statement.
solution to this question?
No, not exactly. I just searched just check answer given. I got the answer as 0. So So just
No,
want
you
to
can check the
understand.
solution because there are examples. Each statement has a counter example. So none of the examples are true. None of the statements are true. And there is in the solution, if you check, there is a function for which all this is checked. You can
Yeah,
check
okay.
the solution.
Okay, okay.
Okay, if there are no more questions, then maybe we'll close. All the best for the end term. Shubham is
Thank you,
also
ma'am.
here. Shubham, you want to tell something?
We want to thank you. It's a very high quality support. Thank you very much.
Yeah, that's. Thank you.
Thank you so much.
Thank you very much, madam. Thank you.
A lot.
All the best for the end term and for your future courses as well.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
So much, ma'am.
Hello, ma'am.
Yeah.
Ma'am, when we will say that directional derivative does not exist?
So the directional derivative is that limit, right? You calculate a limit. If that
Yes,
limit does not exist, then the directional derivative does not exist.
Okay, ma'am. When we will say limit does not exist is in
Along two
denominator.
different paths. No, along any two different paths if you get two different values.
Actually, here we will not use that, no, ma'am. We will use that mx and m root x.
Yeah. So if you
So,
do that and then if you get m in the answer, it means as you vary m, you're going to get different answers, right?
okay, ma'am. Ma'am, in the numerator 0 and denominator h we get 0 by 0 form also limit exists or limit does not.
If numerator is 0 and denominator h you get, even before evaluating h, your answer is 0.
Okay. So, okay, ma'am. Okay. If
Even
I
before
get 1 by
evaluating
h,
the limit, if you get 1 by h, then it's infinity. Limit will be does not exist.
oh, okay, ma'am. Thank you, ma'am.
Just a minute, sorry. When you said 0 by h, it's already 0. Why is it that we would not consider 0 by 0, madam?
Because 0 by h, even before evaluating the limit, what is that function 0 by h?
Anything by 0?
Function, right? Not anything by 0, 0 by something.
Oh, sorry. Yeah. Okay.
After that only you will put the limit. So limit as h goes to 0 of the 0 function is 0, right?
Yep.
Then in orthogonal matrix there are questions, ma'am. So in that concept, how to crack those questions? Most of the questions from orthogonal matrix come in that multiple choice questions. So what
you mean
concept
that
I need to
statement problems, right?
yes, ma'am. Using that orthogonal matrix, what I should remember? What are the concepts? So that is the thing.
So you just remember the definition of orthogonal matrix and then try to solve those problems. There's nothing more than definition that is needed for those kind of problems. So you you think whether the definition will be satisfied, or if it is an orthogonal transformation, will this happen? Things like that. So in those kind of problems, just the definition is enough.
In some kind of problems, what it is given, if A and B are invertible, they are multiplying it at that time. I will be searching for examples of A and B and multiplying those things, whether that multiplied product is again satisfying. That is the approach I need to do.
So first of all, you need to get a feel of whether that option is correct or false. So if it is correct, then you have to somehow try to prove it. You shouldn't look for examples. If it is false, only then you should look for examples. Because if there is one set of values for which that statement doesn't hold, then it is false. But just because it holds for one set of values, you cannot tell it is true. It has to hold for all values. Only then you can tell it is true. Yeah.
Okay. So I need to be thorough with definitions and think according to it.
Yeah.
Thank you so much, ma'am.
Ma'am?
Yes.
Sorry if I can ask a last question.
Sure. Please go ahead.
And there was a statement given somewhere that there is a vector consisting of V1 to Vn in an orthonormal basis of an inner product space V, and then any vector V can be written in the form of V comma V V1 into V1 in that braces,
Yeah.
and plus v comma v2 into v2 and so on to vn. So will it be true or false? So I am not able to prove it. I know that the inner product will be 0. That much I know, and I am not able to proceed it somehow.
Okay, one second. So you have an orthonormal basis, right?
Yes, ma'am. Yeah.
And you're telling any vector v can be written as this. V with vi,
V1.
vi.
Yeah, vi. Yeah, yeah.
Like that. Are you doing BSc in maths?
No, ma'am.
What is your background?
I'm doing engineering.
Oh, okay, fine. So for the questions that you ask, it's actually very good. In the sense, you're asking BSc math level questions, so that's why I asked.
I'm just
So out
because
of
of
interest,
you.
you study, is it?
Yeah. That's correct.
Okay,
I've told
one
you
thing
in the
is,
previous session as well that I've got a lot of interest in mathematics because of you guys. Otherwise, it wouldn't be possible. Yeah.
okay. So we are organizing a one-day workshop on August 20. So maybe you should attend the talks that day.
Sure, ma'am. I will.
And if you're interested in giving a talk, we'll circulate a form after the end term. You can fill that as well. Any basic topic also you can choose, and something that you found interesting in mathematics. Anything you can just give a talk.
Okay.
And what will be the workshop? What will the workshop be on?
It's just a workshop on mathematics. Means we just want to promote mathematics kind of, if you are interested in.
Yeah. So we
Okay.
can
Is it
discuss.
only in person, madam, or is there?
No,
any
it's online. It's completely online.
Yeah. So, ma'am, we can discuss on any topic as well, right?
Yeah, there'll be a few profs who are giving talks, and then talks from instructors and talks from students as well, if you're interested.
Sure, ma'am. I will attend.
Yeah, the details and all will be circulated after the end term.
But this online session is really helpful. All the instructors, they were very
helpful,
very dedicated, actually. Very sincere, very dedicated, and more sincere than the students.
Okay, so Ayush, now tell me,
Yeah.
this is what I want to prove. What can you tell? V in V, I know. What is the next step you can do?
Maybe I will write it in the form of alpha 1, that linear combination type of thing. Alpha 1, V1, Vi comma Vi kind of thing, plus alpha 2. And then from first or second one, it will be 0, the inner product.
So what is the inner product that you will take?
If I consider V1 to Vn, then I will consider V1 comma V1, then V2 comma V1. Then
No. You already have a representation. So think along these lines. You already have a representation.
Yeah. So V1 comma Vi.
No, this is V comma Vi.
Okay. So V
so
comma
this
Vi.
vector V, along with Vi, what will you get?
Yeah.
We get only alpha 1.
Only alpha I, right? Vi. So
Alpha I. Yeah. Alpha I. Yeah.
That's it. You've proved, right? What do you want?
Okay. Yes, ma'am.
There's nothing specific about I. Means this is for all I.
Okay. This is for all I. Yeah. I didn't focus on that part. Yeah. Thank you so much, ma'am.
Ma'am, these alpha i's are basically projection. Are they? Or the coefficient?
You're already on V, and all these are also on V. So
I think we can't comment like.
Okay, one thing you can tell is this. Okay, projection along Vi, that you can tell. Projection of this vector along Vi, along the direction Vi will be alpha.
That we can surely can say.
Okay.
Because the projection will basically be this, right? Vi comma Vi, but since it's an orthonormal basis, this is 1.
Okay.
Yeah.
Okay, ma'am. Thank you so much.
Yeah. No problem.
One suggestion.
Yes, sir.
In 3 months, the content is too much. These all new topics.
Yeah, agreed. But yes, we have tried, Professor Sarang has tried it in the best way possible to maintain the flow and give the important thing and all that.
No, honestly, that way I think you really, when I see the chapters, the way you built them, it is very nice.
Very
It
nice.
is just that coping with that levels every week and then that's the part. I mean, like the last 8, 9, 10, and 11 were basically, they went in a jiffy and it's just over.
Yeah, maybe you were all in the hangover of weeks 1 to 8, or probably happy that you survived it. That 9, 10, 11.
I was devastated, particularly about the quiz 2, and immediately after quiz 2, there was this 9, 10, and 11. And yes, you gave us time, but getting out of the lack of performance there and this, yeah, it's more of what I was not able to manage with my work also going parallelly.
Yeah.
That's the thing.
Understandable.
Yeah, but the way you
this is
built
what
it up
the
is
course demands. Means.
Yeah.
The number of new concepts is overwhelming.
No, the concept is not new, calculus at least, but time is not there to practice.
Actually, it depends upon our background, that which background we are coming from.
But as Ravi told, 9, 10, 11, even though it's easy, you couldn't invest time.
So Krishna sir, you would asked at the start, right, if you can skip 10, 11. So I was telling that only, like what if a problem starts with tangent plane, like the previous n-term problem, right?
Yes.
You know everything after that, but you don't know the answer to the first question. So you have lost everything, right? So at least the formulas you...
Yeah. So planning to cover that, yes.
And the formula overload in the last 3 was also rather high.
Santosh sir, can you please mute?
That's how we should learn.
Can I mute only him? That possible?
No, ma'am, you should mute all.
No, I could do just one. Okay.
So it's 9, 10, and 11 that will be
would...
critical for ML, I mean data science, right? That is where you are actually talking about planes and surfaces and gradients.
Yeah. But the vector, the linear algebra part is what will continue in MLF. Means the tangent plane part will carry on it will come somewhere, but
so 1 to 8
linear algebra, continuation of linear algebra is MLF.
Okay.
So first
focus will be on that only, yeah.
1 to 8
diagonalization and SVD.
Yeah.
But overall, this model of education is much better than the brick and mortar type. It's empowering. At least it's fine.
Ma'am, it's amazing how all 3 of you have been so dedicated, and how you come up with examples, at the spur of the moment. And for you particularly, your speed of calculation is so amazing that by the time I try to understand what you've just calculated, you've moved on to the next one.
Oh
really
my
amazing.
God, that's not a good thing.
Speed is very high in calculation is amazing.
Okay.
No, actually, this online session helped a lot. Actually, otherwise it would have been
amazing. Maybe from my point of view, but from your point of view, definitely.
No, ma'am, but you cleared every doubt of every people that you listened.
Okay.
You should consider maybe, ma'am, some course in diploma as well.
Actually, I don't have time to study courses there and then teach there, so that is the problem.
But you could have made the calculus.
But I think you guys can teach in MLF. because you guys have such a beautiful concept of mathematics.
And
Maybe we
will
try it sometime.
statistics will be handled by mathematics people, or how? Because that
No,
will be better
actually,
actually.
not all math people are good in statistics. Like if you ask me, I know nothing of statistics. So when we study BSc in mathematics, we have only 1 or 2 papers in statistics. So there is a BSc in statistics, a separate course altogether.
We'll first come out of maths, then we'll see. Okay, thank you very much.
Yeah.
Okay, ma'am. Thank you very much.
Thank you, ma'am. Thank you very much.
Thank you.
Catch you. Bye.
Thank you.
All the best.
Thank you. Bye.
Ma'am, thank you so much. Please do come in
Thank you.
120th wala session.
Yes, sure.
Thank you, ma'am.
Thank you.